Good afternoon. So we have the graveyard slot with Logan, but I hope that you will find this presentation interesting. Anyway, there is a bit of a surprise at the end, so that should keep you interested and awake. As you know, I couldn't come to a conference without speaking about contaminated runways, and Airbus has been one of the early adopters of the proposals of the TALPA ARC. The TALPA ARC was concluded in 2009, and it was implemented by the FAA in 2016. But we already issued our performance data to all of you in 2012, which means that you were all guinea pigs volunteered by Airbus of these new concepts. When we look back, in fact, this entry into service of these new concepts has gone pretty well. And I know that some of you in particular may have encountered issues along the way that we have dealt with together. And now the industry is catching up with us, and we have both the ICAO and EASA that are implementing these principles in their standards and in their regulation. But even so, not all of the issues are fully addressed, and the last winter was another opportunity to identify some things that we need to think about and solve as an industry. And the aim of this presentation is thus to look how far we've come, look what is left to be done, look how we are helping you, and also to make an announcement. So first let's look at the TALPA. If we go back in history, in 2008, for example, before the TALPA recommendations were published, you could see reports like this, and in fact, this is still a report that is conform with the current standards and reporting formats, and it's fairly recent, in fact. And this report gives a lot of information. So in this case, we only have a part of the runway that is cleared. It is 40% bare and wet. It is 50% wet snow trace, and it's 10% compact snow. And we have the edges that are covered with dry snow. A lot of information for our 2008 flight crew that's trying to now enter this type of table to do their computation. And this was obviously not an easy call. It was not easy to make a relevant assessment. And on top of that, the distances that we published were not as operational as they are today. That is why we implemented on top of that, even though we had a principle of reporting what the inspector would see. On top of that, there were initiatives trying to give an information that was directly relevant to performance. And because we're in Canada, I have to talk about the Canadian Runway Friction Index, the CRFI. CRFI is an interpretation of a measurement made on the runway that results in a number, and this number is intended to be used directly in the determination of performance, at least for landing. However, this looks at only a single criterion, and what we have understood with the TALPA is that we need to have a holistic approach and look at all of the elements. So TALPA addressed this holistic approach by coming up with the runway condition assessment matrix. It's pretty small, and I'm sure you can't read it, but you don't have to. You all have it in your books, and I'm sure you're very familiar with it now. This allows to directly interpret the new type of report that we're going to get from winter 2020-2021. So here I've put together an example for Heathrow, where we have the information such as the runway condition code, the percent of coverage, the depth of the contaminant in each runway third, and the predominant type of contaminant in each one of those thirds. So as I said, the FAA has implemented this already since 2016, And here you have a report, an actual report from Binghamton from this winter, end of this winter, where we have the same elements, so runway condition code, contaminant type and depth, provided to the flight crew. What do you do with such a report? Well, you can directly use the runway condition code in your FlySmart application, select the appropriate type of contaminant, so in this case 2 for medium to poor, and you obtain your performance calculation. What if the inspector in Heathrow now thinks that the runway is acting worse than the slush, which is nominally in the category 2? He can report a 1, and similarly the pilot can adjust his performance to that poor performance, to that poor braking action, immediately, directly in the application. So much easier to do, and for landing, we think that we've got pretty much all bases covered. We are able to make any use of any information that is being given. For takeoff, the situation is still not quite as perfect. We have, in Europe at least, got a regulation that clearly says to us that we need to calculate with contaminant types and depths, and the reason for that is that at least for those contaminants where we have drag involved, we have to take that into account for the acceleration and the deceleration phase, and depending on the conditions, either one of these two could prevail in the determination of the takeoff weight limitation. So we can only use, in fact, one of the columns of the runway condition matrix for takeoff. And we can rapidly, easily find reports, real reports. So this one is a report from McGrath in Alaska. It's not really a runway that we typically would go to with any of our aircraft, but it's just an example of the type of report that you can see. We have a temperature which is which is above minus 15 degrees. We have compact snow, 100% coverage. That should be in category medium, and so we should have a calculation with runway condition code 3. The report is with a runway condition code of 2. We've seen for landing that's easy, we just select the 2, but what do we do for takeoff where we don't enter with a runway condition code? There's in fact no direct solution available, and I have been contributing to a manual written by ICAO, which should be released at the end of this year, which says that in that case, your computation with the basic contaminant should be okay because the exposure to rejected takeoff is fairly low. So if you use the full runway and reduce your crosswind limits, you should be fine. At Airbus, we are not quite satisfied with that approach. So we think that we need to have some accountability for the right type of contaminant. So in the EASA working group on the rulemaking, we are pushing for better solutions on this. Another aspect is that even when the reported contaminant is in line with the runway condition code, we have a list of contaminants in this matrix that is not necessarily available in your software or in your performance tables. This is because the prior performance certification requirements did not include, for example, dry and wet snow performance, and we did not have any performance models for that. This is all calculated performance, nothing is demonstrated as such, and so without a performance model, we cannot generate performance, and there's a gap in trying to address all of the situations. Again, we are making improvements. We are extending the temperature ranges for the computations, and we're adding the missing contaminants for which models have now become available. But we still have a couple of contaminants, like the compact snow that we just discussed at higher temperatures, and slippery when wet, for which there is no standard in the industry. And this is being addressed again in the EASA rulemaking task, so we should have an opinion issued by the end of the year on that. Another issue that has come up in this winter, and this is one that stood out in terms of the questions from customers this year, was that of layered contaminants. We have a lot of reports, and especially from one particular airport, Oslo in Norway, where they were frequently reporting layered contaminants. So 4.7 stands for dry snow on ice. If you want to find this contaminant in the runway condition assessment matrix, you have to move down further than for the area for which we actually provide performance. It's down here in the less than poor or nil category. That means no performance information is provided, and in principle no operation should occur. However, these are actually pretty good runways, and they are reported with braking action 3 for landing. In fact, they look like that. What the inspector wanted to try and communicate was this situation. So you have the main picture, which shows you a close-up of the actual runway, and you see what it looks like from the cockpit. What happens here is that they are brushing the snow, and it melts into the macrotexture and refreezes there. So there's ice on the runway, but it's not what the tire is in contact with. The tire is in contact with a relatively clean runway that is covered in a light dusting of snow. And so far, we have not come to a final conclusion on how to address this, but a workable solution has been used by several operators in the last winter by applying dry snow performance, and this was appropriate because it allowed them to operate and at the same time make a realistic assessment. On the top end of the scale of winter runways, we find specially prepared winter runways. We have some operations in Northern Europe, at least, where operations are based on the necessity of having at least a runway condition code 4 in order to be able to carry the desired payload year-round. So they have conditions of large minus Celsius degrees for several months, during which it is difficult to remove the contaminant entirely because the de-icing fluids typically become inoperable below minus 7 degrees, and they actually create more slippery runways and are difficult to remove afterwards if you use them at very low temperatures. So they just have to live with the ice on the runway, and in order to do that with a good performance level, what they do is that they fix frozen sand to it. It's an onerous process. It uses thousands of tons of literally gravel each winter, but it allows to get back to runway condition codes of the order of 4. And EASA has accepted to allow this type of operation if the airport can demonstrate with aircraft data that such good frictions can be reliably achieved. On the other end of the scale of runways, we have slippery when wet. This is a standard that has officially now been introduced by ICAO. Questions remain open on how we report runways that have been contaminated with rubber or have polished aggregates, and where in wet conditions the friction drops below the level that is expected in the performance computation and can thus create surprises for the users. In fact, most of the accidents and incidents that we see in the industry now occur on wet runways and not on contaminated runways. So progress is being made, but it is laborious. In order to address this situation, where we don't fully understand why friction on wet runways can drop off very suddenly, we have put into place a procedure that you are hopefully familiar with in the FCOM. And it asks you, when you are evaluating the performance on a wet runway, to make a cross-check to identify whether you can operate without using reverse thrust or not. And this cross-check is made with an in-flight landing distance computation with medium to poor braking action without the reverser. And if you can achieve a stop on this runway, then you're allowed to run this operation without you're planning it without reversal. The reason behind that is that during the accidents that have occurred, there was typically heavy rain, and this led to this. This was involved in this sudden drop-off of the friction, but there is something, a characteristic of the runway, that is also involved that we may not necessarily know about. And this procedure should really be applied whenever heavy rain prevails at the destination. So we have now seen how far we've come. We've also seen that a few things are still left to be done, and that even though we have better performance assessment, the environment can still surprise you. And to address this startle factor that we have seen with Florence on Tuesday, we have now a system available, the runway overrun prevention system, about which I would like to speak a little bit. So the ROPS is a system that I'm sure you have now heard about, because we have been talking about it in a lot of conferences. It makes an assessment of the energy of the aircraft during the approach in order to decide whether you will be able to make a safe stop. It is divided in two phases. The first phase is the airborne phase, up to a transition on the ground, where the system is go-around minded, and it will give you alerts like if wet, runway too short, or runway too short. And then there is the ground part, during which the system is stop-minded, where it will give you indications on how to maximize your deceleration. So this system is now actually installed on many Airbus aircraft, and we have already got 1.72 million landings with this system. It is installed on over 1,000 aircraft by 68 airlines. So we now have a very significant exposure of the system in service, and it's generally working well. But like any system, there were some teething issues which I would just like to quickly talk about. And the message I would like you to take away from this is that all of the known issues have been fixed. So what sort of thing have we seen? We've seen the loss of ROPS. There are two reasons for this. One is that the aerodrome or the runway data may not be in your database, in which case the system cannot make a prediction, or that there is an issue with the GPS vertical position, so the positioning of the system for the energy determination becomes unreliable and the system becomes lost. So both of these can be addressed. For the aerodrome data, NavBlue can assist you in dealing with the providers in order to update the databases on your network. And for the GPS vertical position, a fix is available. The nuisance alerts that we have seen in service are divided in two kinds of categories. One is the low-speed alerts. Most of these were associated with a runway that had a shallow turn at the end onto the taxiway, and which the operators or the flight crew were approaching at relatively high speed. The system does not know about this taxiway, so all it tries to do is to stop you before the declared end of the runway, which it considers like a brick wall. And so it would generate alerts of max braking and max reverse at the end of the landing roll, when the flight crew was in total control of the situation. So this has been addressed by changing the conservatism of the runway end protection and adjusting the thresholds for the warning, and so they now have largely disappeared. The other category are the high-speed alerts. We have typically seen these on long runways that were dry, and obviously there was no issue with stopping the ability to stop the aircraft on the runway. This was again due to some very conservative thresholds on the alerts and those have been addressed. So all of these fixes are available, and if you want to retrofit your aircraft to these standards, I would invite you to talk to NavBlue to find out what these standards are. But besides fixing it, we are also making it better. One step is on the A350, the coverage of contaminated runway conditions. As you have seen in the first slide on the ROPS, it currently on the A320 and A330 only addresses dry and wet runway condition. On the A350, we have a runway condition selector, which allows to select the runway condition code or the runway contaminant type on the ECAM, and to then have a protection that is adjusted to this runway state. On top of that, during the flight preparation, the system will show you which runway states do not allow a safe stop under the forecast conditions. On the A320, A330, we are moving to improve the system by also introducing a runway condition selector. In a first step, it will only allow a selection between dry and wet, but this is already a step forward because it removes a conditional alert that we currently have, which is if wet, runway too short, which means that we have relatively complex flight crew procedures associated with this alert. An alert should be clear and only allow one interpretation, and that will be possible with this change. So we have now seen how we are trying to better understand what really the runway is like before we're doing the operation. We also have seen how we're addressing the surprise element when the runway behaves different from what has been reported. Now, to close the loop, I would like to invite Logan to present you Runway Sense.
All right, thank you, everybody. So I'm already getting the sign that we're going to have to speed this up a little bit. But I'm very excited to be here today. So my name is Logan Jones. I work within NavBlue. And I think what I'm going to show you today, it shows you the power of the collaboration we can have between Airbus and NavBlue. This is a project I've been working on for about 8 years. 8 years is a long time. 8 years ago, I couldn't grow a beard. And now look at me. So Lars presented, what we've been doing on runway safety, but there was one key element that we felt has been missing. You're using the information to prepare your descent with FlySmart. You're using that information with ROPS, but what if the information itself that you received was not correct? What if the information was out of date? And so when we looked at one of the key things that we needed to do to close the gap on runway safety, it came down to the runway condition information. So this is a survey that was done back in 2002, but I think it's just as true today by Canadian pilots. And when asked what information needed improvement, you had 80% of them saying the frequency of updates about the runway condition, the use of PIREPs, the timeliness of getting values, and the accuracy of values. I just want to read 2 quick extracts from a couple of incidents that have happened in the past. So we have this one. It says 1 minute prior to landing, the air traffic service provider passed a braking action of medium for the entire runway to the crew. The analysis of the FDR data conducted by the aircraft manufacturer after the accident indicated that the braking action was poor or worse during the landing. And the second one, friction coefficients on the runway were measured immediately after the snow removal. The braking action in the snow tam announced at 22:07 that it was good across the runway. 20 minutes later, based on QAR data of the accident, the runway conditions were such that the braking action was between medium and poor. So in all these cases, the flight crew had done the right things. They had prepared their approach, but they didn't have the right information. And so we've been working on how to solve this issue. And after 8 years of research and technology, we started to say, how can we build a more connected aircraft? How can we share the information? And why can't the aircraft itself measure the friction and report it to the whole airspace community? So this is what we've developed.
bar.
Our Airbus 271, the measured braking action after landing was good to medium.
So this is what we're calling Runway Sense. So you may have heard it in the past when it was presented as a research and feasibility project. It was often called Corsair. Now that it's ready and it's out there, it's going to be called Runway Sense. And there's two very key parts to this, which is that collaboration between Airbus and NavBlue. On one side, we have the onboard software. So this is an ATSU AOC application. It's very small, takes between 5 and 10 minutes to install on the aircraft. And it does exactly what you said in the video. It is completely transparent for the pilot. There is no pilot action needed. It runs in the background. So during the landing, it records the parameters that it needs. And then during taxi speed, it makes a calculation of what was the braking action actually experienced by the aircraft. You'll get the display on the MCDU, which I'll go into the next page, and that allows the pilot to use this information. It's an objective information to help them with their pilot report. But on the same side, we send a data message to the ground with the result. And this is where the real power comes in, because now it's not just one aircraft. It's a collaborative web platform. This is Waze for your aircraft. So when I get in my car in the morning, I open up Waze and I'm connected to 1,000 other drivers. I know where the traffic is, I know where the crash is, I know what to avoid. The same principle applies here. We want to crowdsource the information from the aircraft about the runway condition. The more people that use it, the better the platform becomes. So this is what it looks like on the ATSU. You'll see there's a new menu item here called braking action. Again, it's only going to be available if there was a slippery condition encountered. On clicking on that, you get the information directly here where you can see the full rollout of the aircraft and then the average braking action that was experienced. So in this case, we have a good to medium braking action over 800 meters. And in fact, during that braking action, what we noticed that there was one small part of the runway, 100 meters, that was in fact poor. So we can detect local degradations. So even if the average was good to medium, we detected there was a small part of the runway that was poor. And this information is extremely important for the airports to know not only when, but where on the runway these degradations are happening. The last bullet you'll notice there is free of charge. So that, again, was a collaboration between Airbus and NavBlue. We said the only way this system can bring the safety benefit is if it's adopted by everybody, if it's free of charge. We need to crowdsource the information. We need a mass adoption of this technology. So the only condition is it's free of charge as long as you agree to share the ACARS messages with us, NavBlue, and contribute to the collaborative platform. So we'll take a quick look at the collaborative platform. I have a working demo on my computer if anybody wants to see it in real time. But this is what an airport would see. So in real time, this would be populating. This is just an example of Denver Airport with 6 runways. And this updates in real time to say, okay, we just got a good to medium braking action on runway 16 left or on runway 16 right. They can then click on the information and we can GPS locate exactly where these braking actions were happening on the runway. And so with every landing that's coming in and reporting, the airport themselves are getting a real-time view of, okay, the runway started out good. We just cleaned it. 10 minutes later, it's snowing. It's degrading down to good to medium. It's degrading down to medium. And the airport now has that information to make that strategic decision. Okay, let's talk to ATC. ATC, in 15 minutes, we're going to have to close this runway. We see that it's trending downwards. So this is a benefit to everybody. This is not just the airlines. This is the airports, the ATC. Having information at their fingertips of what's happening right now on the runway was something that never existed before. If an airport wanted to know what was happening on the runway, they had to say, okay, close the runway, let's send out the friction tester. Let's send out somebody to measure it. Now the runway is closed for 25, 30 minutes. Now they have the information at their fingertips. So where are we today? So again, there's a software and there's a collaborative web platform. So on top, the software, after 3 years of in-flight testing with several partner airlines, we are certifying the software this month. So it should be ready this month. After that, we're going through a controlled entry into service with partner airlines. This partner airlines is still open. So if this is something you see that can bring a real benefit to your operations, if you experience contaminated runways, contact us to be part of this controlled entry into service. It's going to last between 6 to 8 months. At the end of that, then, early next year, the service bulletin will be available, again, free of charge, in the Airbus catalog. On the collaborative web platform side, as you saw, we already have the working prototype ready. The system will be built out in June, and then again, we also need to partner with the airports. They need to see how this information can be of use for them. How can they use this to benefit their operations? So we'll be conducting trials with partner airports over the next year to show them the value that this sort of new information can bring to their operations. So that's it. I think what we've shown here today is that we've been working now for 10 years on this runway safety topic. Lars talked about all the work that has been done in Talpa, about using the FlySmart with a runway condition code to really prepare your descent. We've developed ROPS that can take into account any last-minute changes. And now with Runway Sense, we close that loop to make sure that everybody has the right information about what's happening on the runway. Thank you very much.